Hello, everyone. In this lesson, we're going to go over some examples as how to find critical numbers. First of all, we have studied Fermat theorem, okay? After we study Fermat theorem, we understand critical numbers are important because those are the candidates for local max, local min, and then absolute max, absolute min, even though not all critical numbers will lead to an extreme values, but some of the critical numbers are the candidates for our desired extreme values. So here we're gonna go over some examples as how to find out the critical numbers. And we understand, first of all, the critical numbers. So let's see first, what are the things we need to check? A critical number of a function, right, must be in the domain of the function, right? So we understand that the critical number C, right? So critical number C must be what? Must be in the domain of F. All right. And secondly, there are two categories. One category is that the derivative is the derivative function at C is 0. And the other category, so it's either or. The derivative at the function at derivative at C does not exist. So these are the two categories. The 1 or 2. And we also understand that if it's differentiable, if a function is differentiable, and the derivative is not equal to 0, then those points are not candidates for local max, local min. Okay, so with that understanding, let's take a look at these examples I found from your homework. Okay, the first one, we encountered a polynomial. Okay. As a polynomial is defined everywhere, is continuous everywhere, it is differentiable everywhere. So we don't have function, we don't have numbers that we don't have the second category where the derivative does not exist. So in this case, it's pretty straightforward. Okay. We take a derivative, right? So we find f prime, which equals to, in our case, 6x plus 1. And we set it equal to 0. Set the first order derivative equals to 0. And we got x equals to negative 1 over 6. Okay, so this is a critical, C is a critical number. So the critical number is negative 1 over 6. Whether you use C or not, it doesn't really matter. Okay, as long as you explain what this number, what this number is about. And second and third, right? All of these work may involve factoring. These work involve factoring. Okay, that's one of the major works that you're gonna, when you work with polynomial or work with rational, we're gonna see different types of questions. Okay, we're gonna see different types of questions. All right, so I'm going to bring these concepts with us for our reference. Okay, so you can use them. Okay, and it's also easier, also convenient for me to explain. And this is a polynomial again. So to find it's differentiable as many times as you wish. So we're gonna go find the derivative of the function, which is going to be 12x raised to the power 3 plus 24x squared minus 48 times 2, that's 96. 96x, right? And then we're gonna have to find the critical number. Usually you just set it equals to 0, right? We're gonna solve the equation. So now we're gonna solve for x. Solve for x. And the major technique here we use is factoring. Okay, from this equation, we're gonna factor out the common factors. It looks like we can factor out 12. Right, so if 12 can be factored out, we get, we can also factor out the x, right? So, and we'll have x squared plus 2x minus 96 divided by 12. What does 96 divided by 12 equal to? 96 divided by 12. Divided by, whoops. Divide by 12. Wait, divided by 12. Equals just 8 or 6. Simplify 8. 8. All right. Equals to 0. Right. And at the same time, you want to check back and forth, back and forth. And the factor one more time. What's inside the parentheses can be factored into x plus 4 multiply x minus 2. And here we go. Here we go. And we set it equal to 0. And what do we get? Right? We principle number 5. So x equals 0 or x equals to -4 or x equals to 2. Right? So we have 3 critical numbers. So the critical numbers are, right, 0, -4, +2. Done. Finish for the task. Example number 3. Right? Sometimes we don't use x, we use t. And in this case, it is still a polynomial. Okay, so we're gonna define the derivative with g prime of t equals to 5t to the power 4 plus 15t squared and plus 50. Plus 50. Knowing that we need to factor, and by this time you probably would factor already, right? So I have 5t. No, we cannot factor out t, sorry. We cannot factor out the t, but we can factor out the 5. So we get t to the power 4 plus 3t squared plus 10. Okay? But how do we factor this? It's a fourth power. But the good news is that you have t squared and t to the power 4. T to the power 4 can be viewed as t squared and then squared. Okay, so t squared and then squared. The factoring can be done in the following way, right? 10 is equal to 2 times 5. We got 5 factored out outside, so we have t squared So this is n equals 2 times 5. Did I copy the question incorrectly somehow? It should be able to factor. Okay, so let me double check. No, actually, we're good. It doesn't factor so easily. So this is 10, this is t squared. It looks like the derivative, if it doesn't factor, okay, don't panic, don't panic. I did not copy the question incorrectly. I'm double checking. Okay, t to the power 5, t squared, 5 to the power 3 plus 50t. And we got 5 times t to the power 4 plus 15t squared, 15t squared, no problem. I got no problem. I factored out the 5. And I would just bring back the t to the power 4, okay? Because at the beginning, well, initially I thought, okay, 10 equals 2 times 5. But we're not going to be able to factor this. We're not going to be factor this. But that's not the end of the world, because let's take a second look of this question. Let's take a second look of this question. Think about it. The domain of the function is all real numbers. T squared is always, t squared is at least 0. T squared is at least 0. T to the power 4 is also at least 0. So these two pieces are at least 0. And plus 10, that's going to be positive. And times 5 is going to be positive. So this whole thing is never going to be 0. It's positive forever. So that means there's no solution. Okay, so I'm going to put the reasons here. Okay, if you set a g of t equals 0, there's no solution. And that means there's no critical numbers for this function. That means it doesn't have, if we have no critical numbers, then we can be certain there's no max nor min. No max, no min. All right? All right. A different type of question now. A different type of question now, okay? So this is example number 4. Example number 4 is a rational function. So we need to know the domain of it, right? Because the critical number has to be in the domain of the function. And what is the domain here? Domain is that x cannot be equals to half, right? You said 2x equals 0, 2x minus 1 equal to 0, right? So that's what you get, right? You said 2x minus 1 equals to 0, and then x equals to half. But that's making denominator equals to 0. So domain x cannot be half, okay? So assuming you know how to do that, and I'm sure you know how to do that. Next, derivative, okay? So don't find the derivative. We're gonna have to apply a quotient rule. P of x equals to, we have a, in your mind, you have a denominator being squared. If you call it g, no problem. Okay, no problem. That's your g. And you differentiate the top, we get 2x multiply 2x minus 1, subtracting x squared. Okay, x squared plus 2, and differentiate 2x minus 1, so we get another 2. And we simplify. We're going to simplify the top. Okay, we're going to simplify the top. Where you want to put it down, you write it down. vertically, okay? We're gonna multiply the top, 2x times 2x, that's gonna, 2x squared, that's gonna be 4x squared. Right, we distribute 2x times 2x, 2x times 1, that's minus 2x. On this piece is 2x squared, and 2 times negative 2 is a minus 4. It's a minus 4. So simplify minus 2x squared, take away 2x squared from 4x squared. And we got 2x squared minus 2x minus 4. Okay, so let's double check. This is the place you do wish to double check. You do wish to double check. So 2x times 2x, that's 4x squared, minus 2x. Minus 2x squared minus 4. So we got 2x squared minus 2 minus 4. We are good. Factor out the 2 is on the top. So this 2 is gone. This becomes 2. And now we can factor the top. I mean the numerator, right? That's going to be x minus 2 times x plus 1. X plus 1. All right. And now we can set it equal to 0. Okay, so we're going to set the function equals, the derivative function equals to 0. Okay, we're doing all of these in the domain of the function p. Okay, remember that? So when we set it equal to 0, we know we're operating inside the domain. Therefore, the denominator is guaranteed not equal to 0. And so if we set the function equal to 0, the only thing that's possible is that numerator has to be 0. Right? If we set p, the derivative equals 0, numerator has to be 0. If numerator has to be 0, then x equals to negative 1 or x equals to 2. So we got 2 critical numbers, but we need to check. We need to double check. Okay? Is there a number that the derivative is not defined there? Okay, so we got 2 critical numbers already. We got 2 critical numbers, which belongs to the first category. The second category, we want to see if there's additional number that will cause the derivative is undefined there. Well, now what we see here is that the domain of the derivative is the same. It's the same as the domain of the original function. And therefore, there's no additional numbers. So in the end, the critical numbers are negative 1, and 2. And we're done. All right. Okay, that's example number 4. Let's look at another type of question. Okay, we're done with 4. Let's look at 5. This kind of question, okay, can be very interesting. Okay, so we got the critical numbers, right? All right, so first of all, before we start, we need to decide what the domain of the function. Well, the domain of function, we're taking 5th root, right? We're taking 5th root, and the power is 4/5. The domain is all real numbers, okay? Domain is all real numbers, no problem. No problem. Negative infinity to positive infinity. So far, all of our critical numbers are in the first category. So let's see what's going to happen here. So we're going to find derivative function, and we're going to use the product rule. So first we differentiate. Okay, so let's do it this way. Okay, it's the product, right? So we're going to differentiate that part, and we're going to differentiate this part. Okay, just to make sure we do everything right. The power rule on x raised to the power 4/5 is 4/5, and then x raised to the power of 4/5 minus 1. And that will give us x raised to the power negative 1/5. Okay, but we're gonna do that on the next step. Plus, we keep this piece, right? We're applying product rule. And this part is gonna be chain rule. So we're gonna get 2 times x minus 4. And then we're going to differentiate x minus 4. That's going to be 1, right? So now derivative is done. Let's simplify. Okay. And we just mentioned that this operation will give us a negative 1/5. Okay, negative 1/5. And this part we can remove, and 2 we can bring to the front. We must simplify this because we need to solve for the critical number, right? In the derivative chapters, we just, we did not have to simplify to the last minute, to the last simplest form, but in this place, we must, otherwise we will not be able to find the critical numbers. And what is our goal of simplifying? Factored form, right? From the previous example, we need to get to the factored form. With factored form, we can easily find the critical numbers, right? We can easily find the critical numbers. So let's see, what do we do when we have something like this? Please follow me. There are 2 ways to do this. So I'm going to do the way that most of us would be most comfortable with, I think. Okay. So what we do is that we're going to write it as root form. So we're going to write this as a root form. So first, this is a negative 1/5. The first form we can write is take care of this, negative exponent, which is 1 over x raised to the power 1/5. Okay. On this part, you can write it. Or you keep it this way. How about we keep it this way? Okay, we try to make a minimal change. So now we have a denominator. What are we going to do? To simplify, we have to bring them together. So we're going to make a common denominator. So what will be the common denominator, you think? I think the common denominator will be 5 times x raised to the power 1/5, if you like, because I will take care of the fraction. Okay. So I got 5 in this one, x raised to the power 1/5 in the denominator. We don't have that here. So on this piece, I'm going to multiply 5 times x raised to the power 1/5 on the numerator and on the denominator. So I multiply by 1. Anything times 1 stay the same. With that process, okay, I'm going to do simply. Now I got the same denominator as the other one. right? So I can put it here, the 5, just to make it see better. So this is just a 4, right? And I can move that 4 on the top. Okay? We got the same denominator, but before we process the same denominator, bring these two together. Okay, bring this, multiply that. Oops. Sorry. Not like this. Sorry. Let's go to another level. So x raised to the power of 1/5 multiply x raised to the power 4/5. And the same base x, the exponent can add 1/5 plus 4/5. This will be an x. This seems to be a nice reduction, isn't it? So now let's keep going. Let's keep going. I'm going to take the common denominators, right? I'm going to factor out the common denominator here, right? So what I'm going to do is that I'm going to factor something out. So what can I factor out? I can factor out the common denominator. Put it here, right? So this common denominator is gone. So this will be just 1, and this will just be 1. And of course, if it's 1, you can just omit it, right? So this will be 5x. What else can be factored out? X minus 4. Yes, x minus 4 can be taken out. So and here we have 2x minus 4, so I'm going to take one of it out. One of them out. So we're getting closer. We're getting closer. So let's see what's in the bracket, right? So I'm going to take a 4 times x, 4x. So it's a 4x minus 16. And this is 10x. This is 10x. And of course, you could have factored out the 2 and stuff, right? But that's okay. By this time, we're very close. We're very close. Okay? 4x and 10x, that makes 14x. If you want to factor out the 2, you can. So factor out 2, this is going to be 7x, this is going to be 8. Now we are completely factored. So our derivative function, derivative is equal to this piece right here. And you can write it as parentheses if you like, right? Not required. You can keep it as is, but I just organized the forms. But we have a denominator now, right? So what is the domain of this function? Domain of the derivative is x cannot be 0. Comparing to the domain we started with the function, which is all real numbers, we have an additional number for the derivative that's not in the domain. So this x equals 0 will be another critical number because that's where the derivative is not defined, does not exist. So we got 1 critical numbers already, don't forget. But we have 2 additional critical numbers. How do we know that? Because we're going to set the derivative equals to 0. If the derivative is set equal to 0, denominator certainly cannot be 0. A numerator must be 0. Right? Numerator must be 0. So in this case, we get 2 more critical numbers. So x equals to 4, or x equals to 7 under 8. Oops. 7 under 8, sorry. Got it? So in the end, what are critical numbers? our critical numbers, we have 2 plus 1, 3. We got 0. We get 8/7. So I kind of arrange them in this orderly manner. We have 3 critical numbers because 0 is the number where the derivative is undefined. It's undefined. Does not exist. Okay. So now let's look at another example, number 6. Okay. This one actually involves some more, but we have just 4 more questions. So let's get it done. Okay, let's just get it done. Okay. So I'm going to put the definition of critical numbers here. We are almost there. We are almost there. And this one, of course, it involves domain issues as well. Okay, so we anticipate something like that will happen, like the one we just did will happen. Domain or real numbers, because the third root. Okay, I would show you another technique to simplify these kind of functions. Okay, to simplify this kind of functions. All right, we go straight to derivative, right? Derivative is product rule again. Product rule again. Plus that. And we're going to differentiate that piece. And we're going to differentiate the other piece. Okay, so don't miss anything. So set up properly. Okay, set up properly. And next, the derivative of x raised to the power third apply power rule is going to be 1/3. And 1/3 in the power subtract by 1, -1. So that's going to be -2/3. Okay, so I'm going to just put a 2/3, -2/3 right there. Okay, I think everybody got that. On this piece, we're going to apply quotient rule. Quotient rule on this piece, the power, there, 2/3, and this power -1, that's going to be -1/3, right? -1/3 for this power. And we also have to differentiate 4 minus x. That will give us a -1. Okay, don't forget that. Okay. Chain rule by this time. -1 will combine the product, so this is going to be a negative. And how are we going to reduce this? Right? So let me move 2/3 to the front. So we got this. We get x raised to the power 2/3, x to the power 1/3 here. So what do we factor out? Right? We need to factor, we have to do it. Otherwise, we're not going to find the critical numbers. In the previous example, I showed you one technique. And in this example, I'm going to show you another technique, okay, to factor things like that. So first of all, look at the number part. We have 2/3, we have 1/3. So I'm going to choose 1/3. Okay. What part to be factored out? Okay, so we want to factor out x raised to, if you look at these two, you're going to choose the lowest power. So in this one, we already have the lowest power, but this one we don't, right? We don't. So what we're going to do is that we're going to make sure that this piece also has the lowest power. But how do we guarantee the other piece has the lowest power? We multiply by 1. But how we're gonna make this one? We're gonna make this one as with the lowest power, multiply the lowest power with plus. So these two multiply, you have the same base, exponents adding exponents, you're gonna get x raised to the power 0. X raised to the power 0 is equals to 1. So that's the one we're making. Okay, that's the one we're making. So this way that this term has x raised to the power negative 2/3. All right, both have this x raised to the power negative 2/3. And then we have another base, right? We have another base, 4 minus x. You still choose the one with the lowest power, okay? So x raised to the power, 4 minus x raised to the power 1/3 will be the power of choice. So we have it here, but we don't have it there, right? So what are we gonna do? We're gonna multiply by 1 again. This time, how is the 1 made? The same trick, the same trick. You are going to create another 1. The base is a 4 minus x, 4 minus x. Their power are opposite to each other, right? 1/3 plus a negative 1/3, that's gonna be 0. So 4 minus x to the power 0 is gonna be 1. So this piece, okay, let me cross it. So these two pieces are the additional ones we put it in there. Okay, so we multiply by 1, multiply by 1, anything times 1 stay the same, so equal sign is still justified. I know this looks a little bit messy, but right now I want you to write it down, please. If you need to pause, please pause. Okay. Wait, what did I do? Okay. So after this, I'm going to remove these boxes. Okay, you can always replay. All right. So let's see what happens. Let's see what happens. After all of these maneuvering, okay? After all of these maneuvering, let me write another line because I want to keep that line for your reference at least. What does this equal to? That equals to 4 minus x raised to the power of 2/3 plus 1/3. And 1/3 plus 2/3, that's 1. So this piece becomes to the power of 1. If it's to the power of 1, we can omit it. Oh, wait. Did I miss a subtraction somewhere? Yeah. So this is a subtraction. I'm sorry. I'm very sorry. Okay, this is subtraction. Okay, this is subtraction. All right. Let me double check. That's okay. And that's additional. Yes, we're good. We're good. Okay. And now, after this maneuvering here, right? Bring these two together. Bring these two together. Okay, same thing. This still makes 1, right? But these two will make x because we have x raised to the power 1/3 plus 2/3. So these two powers makes 1. So this is just going to be x. Now it's cleaner, isn't it? It's cleaner now. And now we're going to take out, we're going to do the factoring. Now we're going to do the factoring. Okay, so let's see how I'm going to do the factoring. Okay, follow me, replay until you get this technique. Okay, you need this technique. So I'm going to factor out. So I'm going to, at least at this point, I already have parentheses, so I'm going to use a bracket. I'm going to factor out the 1/3, right? So 1/3 is out. 1/3 is out. After 1/3 is out, so this is left with 1 under 2, so this is 2. I want to take out this piece from here. right? So I'm taking this out, factored out. What else I'm going to take out? This piece is taken out, right? This piece is taken out. Taken out. They're all going to be denominators. So now inside the bracket, it's just 4 minus x minus 2x. Okay, we are getting so much closer. Now what do we got? 4 minus x minus 2x, right? So that's minus 3x. Finally, okay? And then we look at the domain, right? If you want to see the domain better, we need to understand that we apply the negative power property. That's going to be 1 over x raised to the power of 2/3 instead of negative 2/3. And this piece is going to be 1 over 4 minus x raised to the power of a positive 1/3. You see? We got denominators, and denominators cannot be 0. So if you like to organize this a little bit better, you can do it this way, right? So these are the things you can do. I would just leave it like that, okay? It really doesn't bother anything. So now we're gonna set the derivative function to be equal to 0. If we set that equal to 0, oh, before we do that, let's check out the domain. What's the domain for this case? Well, denominator cannot be 0, so x cannot be 0. The domain of the function is in all real numbers. Now we have two numbers that cannot be. So x cannot be 0, and we got more critical numbers. X cannot be 4 because we have to guarantee this denominator is not 0 either. We got two more critical numbers, right? Compared to the domain of the original function, we got 2 critical numbers according to critical number definition, right? At these 2 points, at 0 and 4, derivative is not defined. And we're going to have an additional critical number. If we set it equal to 0, the only way for the derivative to be equal to 0 is 4 minus 3x equals 0. Okay, so that will give us x equals to 4/3. So now in the end, how many critical numbers do we have? We have 3. We have 3 critical numbers. We got 0, right? We got 4/3, and we got 4. We have critical numbers from each category. Okay? Example number 7. Let's do them all, especially the last few types, right? Especially the last few types. Let's do them all. Polynomial again, okay? But let's see if this polynomial is any special, right? Derivative of t is equals to 4 times t to the power of 3 plus 3 times t squared and plus 2t. Then this is not a difficult one. So we just have to factor. But this time, okay, I think we might get to learn some more techniques. Okay, so 4t squared plus, I'm factoring out the t, right? So we have 3t plus 2. Okay, I factored out the t, so when I set it equal to 0, when I set up equal to 0, it looks like the inside the parentheses is going to be a little bit hard to factor. Okay, then what do I do? Right? Well, this is a quadratic function. Inside the parentheses is a quadratic function. So let's set it equal to 0 to see what happens. Okay, so g of t, set the g of t equals 0. We start searching for critical numbers, then we get the product equals to 0. And we have already found a critical number already, which is t equals 0, right? And this domain is all real numbers, by the way. Okay, this domain is all real numbers. Okay, that's the easy ones. That's the easy part. But now, from setting it equal to 0, we got t equals 0. We got a critical number, but we also have to solve a quadratic equation. We have to solve a quadratic equation. How do we solve this quadratic equation? Factoring looks a little bit too much. Let's just do quadratic formula. Okay, so do quadratic formula. We're going to first do b squared minus 4ac. b squared minus 4ac, right? Because recall in your algebra class, there's ax squared plus bx plus c equals 0. The solution in order to find the solution, right? We know the solution is equal to root 2a, I know some of you even know how to sing that song, minus b plus minus root of b squared minus 4ac, right? Okay, with that, we're working on b squared minus 4ac to see what number do we get, okay? Why is that? I will show you, okay? So 3 squared minus 4 times a is 4, c is 2. What happens here is we're going to get a negative number. This is a negative. If the discriminant is a negative number, if the discriminant is a negative number, that tells us there's no real number solution here. So this part does not give us any critical numbers because the parabola is above x-axis. It's always positive. Okay. All right. So no real solutions. No real number solutions. Okay. So the only critical number is t equals to 0. Yes, very good, because it introduced another technique for us that we learned from algebra. Okay, so 2 more. The example number 8 is it's a trig function. It's a trig function. Okay, so please be patient with me. All right. So we're gonna start finding derivative from the beginning. The derivative. Addition rule, chain rule, right? So we get a 2 times negative sine theta plus 2 times sine theta cosine theta. All right. So so this one is a minus 2, right? Minus 2 if you like to rewrite it. Right, so this is a minus 2 factor out 2 or negative 2 of sine theta times sine theta, right? So we're gonna factor out. So let me put parentheses here. So we're gonna put the negative 2 here, sine theta. So this whole piece is being factored out, right? So this is just 1 minus cosine theta. Cosine theta. 2 2's are factored out. Okay, the second the inside the parentheses is a negative sign because we factored out the negative 2. Okay, so then the domain is no problem. Domain is all real numbers. All real numbers. So we're not going to have the category of, critical numbers that derivative does not exist. All right, set derivative equals to 0. And then what do we get, right? So this product is going to be 0. Okay, we dropped the constant because it's useless. Okay, it doesn't contribute to anything. And from here, sine theta would equal to 0, or 1 minus cosine theta equals to 0. So we have 2 trig equations to solve. So sine theta equals 0 in the entire domain. How many theta are there? We'll make sine theta equals 0. The solution in here, we have lots of critical numbers. K times pi. K is any integer. K is any integer. K is any integer. Okay, so please refer to the study of trigonometry review on this piece that we get a cosine theta. We got cosine theta equals to 1. So what are those values make cosine theta equals to 1? Well, cosine 0 equals 1. Cosine 2 pi equals to 1, right? And 2 cosine 4 pi equals to 1. So on this solution, we got theta equals to 2k pi. 2k pi. K is any integer, right? If we combine this solution with that solution, if we combine this solution and that solution, k pi include 2k pi, right? Because k pi include pi, 2 pi, 3 pi, 4 pi, and so on and so forth. 2k pi include only the even number of k pi. So the final solutions will be critical numbers. The critical numbers will just be k pi. Any multiples of pi. So here we got lots of